Let's move right into our panel discussion then. The Beyond Virtual panel is up this morning. Our moderator is Barbara Ryder from Virginia Tech. Barbara is the head of the Department of Computer Science at Virginia Polytechnic Institute and State University, where she holds the J. Byron Maupin Professorship in Engineering. Her research focuses on static and dynamic program analyses for object-oriented systems. Barbara is a fellow of the ACM and a 2008 recipient of the ACM President's Award. And in her previous position at Rutgers University, received the Leader in Diversity Award and the Professor of the Year Award for Excellence in Graduate Teaching. So, Barbara, let me turn this over to you. Thank you.
Thank you. Hello. I'm going to make some brief remarks for the panel before the rest of the panelists go. I basically want to concentrate on two technical challenges that I think are the most important technical challenges, or certainly from the systems perspective, important technical challenges that our discipline faces. And then, if I have time, I wanted to give you 2 or 3 scenarios of what life might be like in the 21st century if we can actually solve some of these challenges and develop the technology that will support the kind of lifestyle I want to talk about. So the first challenge is really finally dealing with concurrency. And by this I mean in the field we are really rapidly moving towards using a radically different computing substrate, framework basically. What's happening is that we have desktops now around the room. We have multi-core chips in there. And we have everything from small-scale computers that we can carry around and do our everyday tasks with capable of concurrency, all the way up to the scale of supercomputers that with low-power requirements and in these clusters can actually provide concurrent execution. So what's the problem? This sounds very, very good. The difficulty is that we really don't know how to use this hardware technology. We don't know how to pose problems effectively for solution on this hardware, and we need to really change the way we view computation in a basic, essential way. We need to be able to describe problems, to model the real world, and to solve problems using the idea of parallel computation. And this is going to force people to really do a paradigm shift and really change the way that they teach people and train people to do computer science. So this is the problem. Okay, this is the technology's there, but this is the problem. We're going to need new algorithms, new storage mechanisms, new ways to specify programs, new ways to do software development, new ways to ensure the security and the reliability of the software that's built. And so there's a lot out there, and we're just beginning to chip the surface. So that's my first challenge. Second challenge is how to deal with what I call Firehose data. This is I don't know, I apologize, I don't know the person who originated this term, but I've heard it quite a bit. Basically, we're living in a world with always-on devices. These devices are producing data constantly, and we really need to understand how to deal with real-time computation and what it means. We have mountains of this streaming data coming at us, produced by sensor networks, for example, medical instrumentation. We don't know how to classify this data. We don't really understand how to catalog it, how to record it, how to store it, how to search it for some sort of patterns that will help us understand things, how to aggregate it for human consumption, how to visualize what's really going on, and what this data is telling us. So this second challenge is about how to live in an information-saturated society. And the underlying technologies we need really span across computer science, much like the concurrency challenge. Okay. So now for my two or three scenarios. So first, seeing my gray hair, this leads me from a personal standpoint to worry about what is happening, what's going to happen in the country when the baby boomer generation, of which I am a member, starts aging over the next 20 years. So how can we use our technology to enable a quality lifestyle for our aging population using virtuality. So let me give you some examples. Think about an older person being, or older family being able to live by themselves in a home that has smart devices, that has network accessible devices where loved ones on the net can actually check on them, can actually set the setback thermometers for them, can help them deal with the complications of appliances that younger people have trouble setting, and older people probably will, can check that certain, the furnace is going on, that they're not out of heat, can check that the refrigerator is stocked, or check the quality of the water. We really can do this. We just have to solve the problem of the streaming data, and we have to do this for millions and millions of people, so we have to be able to use concurrency somehow. So home maintenance kind of tasks. What about having an elderly person able to swallow some sort of sensor device that can actually send medical information back constantly to physicians to be able to monitor chronic conditions or dangerous conditions? This is actually, I believe, possible if we can solve the other problems. We also have to address the issue of lifelong learning. I think that as our population ages, there will be a need for individuals to feel they have an appropriate lifestyle, a lifestyle that's engaged in society, and they will want to keep learning things. They will want to be giving back to society to make their lives more meaningful. Already people exchange a lot of information, even if they are not on Facebook necessarily, but exchange emails, exchange photos, have real-time camera sessions on Skype where they see grandchildren that live a nation away. We need to build on that kind of social networking that allows our culture to have families stay connected, and that builds a better environment. And we can think about having virtual teachers, virtual colleagues, virtual companions who check in on people, for example. So I think there's a lot of things we can do. That's scenario one. Scenario two is a medical revolution. So what would happen if we could get access to medical expertise anywhere, anytime? So that's my sort of everyday man or woman's view of what virtuality really means. Actually can have access to expertise. Well, right away, geographic remoteness becomes somewhat eliminated as a problem. You need to see a specialist, you can get to see a specialist, albeit remotely and requiring the sensor data that I talked about before. Lack of funds, cultural differences. A lot of these things might be levelable, or at least made more level, more equal by having the ability to really have expertise available on the network. We could do large-scale real-time modeling of medical problems or medical threats. We could use simulation. We do now use simulation in medical training, and this could even be amplified and made much more realistic so that we can get medical care and quality medical help into areas of the country that right now can't afford it or can't attract them. Underlying this, obviously, the medical professionals have to have access to large volumes of data, to information that can be available from the sensor data and also from the general community, historical data on what has happened in some location or to some individual. Our previous speaker mentioned the electronic data record, the personal electronic records, and that has all kinds of issues, but particularly if we don't have the capacity to do computation quicker and more reliably than we do now, which is the promise of concurrency, it will be very, very hard to integrate into our everyday lives. So how will society be impacted by this revolution? Well, the world will really flatten in terms of access to information and the ability to live a quality lifestyle across the country. Final challenge, and this links back to what we were talking about yesterday. How do we train as educators, because I am an educator, citizenry for the 21st century? I think that the need for fluency, for computer fluency, is equivalent or is I guess, the 21st century need comparable to the need for critical thinking, which was something that many of us were raised on in our college days. The need to be able to evaluate a technology, use a technology, have some mental image of what the technology is capable of and what it's not capable of, to understand the core of what computer science is. the bones of computer science, according to Mary Shaw. She has a wonderful article about what really is computer science when we get rid of all the names of all the different subspecialties. And you talk about abstraction, and you talk about algorithms, and you talk about computation, and you talk about estimating how well something will work. We need our entire population, everyone who goes to college, and we hope that all of our young people will be able to go to higher education after 12th grade. We need everyone to have some facet of this kind of fluency. And we, as computer science educators, ought to be doing this. We should not foist this off on others. Okay, I'm done. Are there questions? Yes. Could you please? Yes, thank you.
Junie from University of Iowa. As an educator in computer science, and the last questions you mentioned is we have to make very clear about the definitions of the computer science, the scope of the computer science. Currently, it is still not quite clear amount with the following terms. What is the really computer science? What is the information technology? What is information science? What is the informatics? All of these terms, and for example, like the previous talk, what is, he cast another terminology, what is information communication technology?
Well,
that's what I'd like to hear about, what people's opinion is. Because once we know these definitions, we can define our scope, and then we can go to the next step.
Okay.
Thank you.
You may have misunderstood what I tried to say. What I was trying to say, I mean, there is some value in doing what you're talking about, because we want to have curricula be appropriate for whichever sub-piece of information technology and communication technology we're talking about. But what I was trying to say is to make an analogy to the way many of us who went to college were at a time when having a liberal education, and this is true today, was supposed to teach you how to read things, how to synthesize them, how to evaluate them, how to judge them, how to be able to come away with the core of the idea. Okay, so that's sort of critical thinking skills, right? Well, I think there are computer critical thinking skills. I think there's an analogy that people, in order to live in an information-rich society, live in a society where technology is so ubiquitous in our everyday lives, people have to be able to understand how that technology is affecting them, what it can do, what it can't do, and have some mental image of what this technology is. And my argument was that I think that we should not foister this off on other individuals in the university. This is something where if we look at the core of our discipline, what is CS1? It's teaching problem solving. I mean, there's all this stuff about all the languages and arguments about how to best do that, but it's teaching, abstracting a real world problem and solving it. Well, that's an idea we have to make sure people understand is part of our discipline. That's what I'm trying to say. Yes?
So does it mean that the fact that all of us are taking drugs, we should become biologists, and the fact that we are driving cars, we should become combustion engineers? Solving problem is not a computer science invention. Problem solving is what makes us human. And I think that we have to get out of the mode of identity crisis. And going out there and saying people must understand technology in order to survive. People have been using stamps and glue without understanding how glue works. So I don't think it's a computer science problem, and we should stop mystifying what we are doing and maybe spend much more time on demystifying it and make it so trivial that you don't need all this stuff in order to live in this society. I think we are spending way too much time in mystifying what we are doing and saying, you must learn computer science in order to survive. I'm a computer scientist, and I grew up playing with wood blocks. Worked for me.
I don't think we have to. I don't think I'm trying to say that you must learn computer scientist like a person who will practice computer science as their profession. I think what I'm trying to say is that there should be a computer science 101 that has some depth, that has some core, that has some real center. And it could be there are other disciplines that have problem solving as a key element of the discipline. But certainly it's a key element of our discipline, particularly when you talk about abstracting enough of the problem away so that you can actually come up with a solution that will have some relevance in the real world. Fran.
I love the set of challenges that you have, and especially resonate to the data challenge and the infrastructure challenge, because in some sense, to get anything going, there has to be a reasonably firm foundation.
Right.
For the NITRD folks and for the agencies, what are some actionable approaches that they can use to kind of start getting at the solution to these kinds of issues?
Well, I think that, from my perspective, one of the things that we've heard here is trying to do computer science in a more collaborative way in order to always have your eye on some practical problem or some set of problems that is the final conclusion of the research. Now, you may be way in the beginning of trying to get together an underpinning or solve some piece of the real-time data surge problem, but there should be some link back to reality. And that may be my software engineering roots speaking. And so I think that by engendering better cooperation between industry, actually, and universities, this will be easier to do. I really do appreciate some of the points that have come up in discussion here about how difficult it is, not because the individual researchers don't want to do this collaborating, but because the mechanisms, the foundational structures impede having close collaboration. And I think industry has a better, even industrial research labs have a better handle on what what some of the real world bottlenecks are to some ideas that you might come up with. So it's very profitable to get people together between academia and industry from my perspective. Yeah.
I wanted to continue on the question that Fran posed. I think creating more interdisciplinary incubators, empirical research incubators in computer science that involves other disciplines is a first step. That's what we have been doing, working with mechanical engineers, electrical engineers, civil engineers, and bioengineers. There are about 15 faculty working in my lab in this area that you just presented. And it has really helped us to understand their physical requirements, their constraints, while we are working on the data to decision to follow Mark's paradigm.
Thank you. I think we better go on. Our next speaker, you're not sitting in the order of speaking, is Bob Kahn. Bob is the chairman and CEO of the Corporation for National Research Initiatives, which he founded in 1986 after a 13-year with the DARPA agency. And with Vince Cerf, he was the co-designer of the TCP/IP protocols and the basic architecture of the Internet. Bob's a member of the NEA, a recipient of the National Medal of Technology, Presidential Medal of Freedom, and the 2008 Japan Prize for Information Communications Theory. We're honored to have you. Would you rather have this one?
Yeah. No, I think what
I think this will work fine this way. Okay, thank you, Barbara, and nice to see everybody here. I'm going to talk about a set of related issues, some of which I got into when Tom was here. One of them is architecture through design and implementation. A second one is infrastructure deployment, achieving critical mass and evolution. And then the implicit issue that I'm raising is all about kind of re-architecture and iteration, which is essentially taking on the foundations, taking on the founding fathers, if you will, basically looking at how you redo architectural things in a fundamental way with all the uncertainty that comes along with that. So let me just say, architecture is fun, at least it is for me, maybe for other people too. Design and implementation, of course, is kind of taking those ideas into fruition. It can be challenging and it can be rewarding. But once deployed, changing an architecture is really hard, bordering on almost impossible in many cases. As I see it, deployment is basically a kind of a construction task. It's sort of getting things out and in place. Achieving critical mass is a different issue. It involves persuasion, hand-holding among early adopters, constant iteration and refinement. And evolution itself is a technical process, but even more so, it's a social and it's an organizational process. Circumstances matter. They matter a lot. You can go through all the analogies about changing engines on a plane in flight, or maybe building space structures at 22,000 miles an hour is a better analogy. But there's almost nothing easy about making substantive changes to a deployed network. Just take the case of IPv4 v6. We're still struggling with that transition. It's turned out to be much harder than people expected, and not only for technical reasons. I personally oversaw what I think was one of the easiest transitions that was ever made in the networking field, which is the movement from the old NCP protocols to the TCP protocols. But even that took many months and a lot of persuasion among people to work with each other and get things done in a timely fashion. And that was with a community of friendly and directly funded researchers. Think about today's internet to get a sense of how the world has changed since then. There were numerous changes to the ARPANET over its 20-year history, but all during that period until the very day it was decommissioned, the basic architecture really remained intact. And with regard to the internet, I think in the 35 years or so that it's been deployed, there have been numerous changes, but the basic architecture there also remains basically intact. There have been calls for new approaches. Various efforts are underway to try and develop new architectures and network design approaches, but it still remains clear just how you go about making such a clean break from the existing structures and still have everything not collapse in the process. So this is a microcosm of the general question of developing information infrastructure on a national or even an international scale. The internet really is a good case study. The protocols there were the easy part, in my opinion. The hard part was determining how to deploy and manage a worldwide technological system in which there were hundreds or thousands of organizations and people participating in developing equipment and software that all had to work together. Today it evolves through a standards process that was designed over time. It was not a single leap of intellectual work, but it was iterated over time with many people and put in place. And about every 10 years it's had a radical restructuring of the process by which things are managed, just to deal with the complexities of what's happened over time. So as the infrastructure matures, I think our experience is that these processes that guide them also mature. And in the case of the Internet standards process, it began back in the late 70s with an Internet Configuration Control Board. By 1983, it had grown top-heavy with observers. There were other structures generated, and many of you know sort of what's come out of that today. But what started out as a grassroots, bottom-up activity driven by leaders in the research community, some government folks and a handful of industry participants, has morphed over time to one that is largely driven by industrial participation with limited university and government participation. Ultimately, cost considerations have played an important role. Who can even attend meetings splayed across the world and often lasting a week long? But the primary driver here, I think, is the need for industry to ensure that its interests are represented in that standards process. And this is a natural thing that will happen with anything that becomes really essential in the society in which we live. So what started out as a very dynamic, flexible structure, eventually morphed over time into a much more deliberative and some might say restricted method of operation, where bureaucratic methods have now taken hold of the process. But it continues to do its job, and it does it pretty well, much like other standards bodies. I think this is a very natural evolution, but in this whole process, there has really been no ability to tackle the basic issue of architectural change. It's been evolution at the margin. So what is the impediment to such fundamental architectural change? In the first place, there's an issue of who really knows enough to do it. Because when you make basic architectural changes, the implications will affect everything. You will infer changes potentially in every part of the whole system. So complete architectural overhaul is almost unthinkable to most people, and yet I believe we have to continue to try because good ideas will continue to flourish. And what was once considered to be pretty good may at some point in the future become overloaded with all the changes and incremental modifications that a real clean break may be appropriate. So what are our options? One, wholesale jettisoning of the old, and as you might do in the construction industry, seems to me is largely out of the question. Unless everybody everywhere jettisons everything at once and suddenly the whole replacement comes up instantaneously. This is not a very likely prospect, and the cost occurs at one point in time, even if it could be done. Secondly, and I'm conscious of the time here, bootstrapping and layering, as we know it works in many cases. In this case, you use the existing infrastructure to sort of layer a new one on top of it. And so eventually you take what's underneath and get rid of it and sort of systemically replace it. So starting afresh is really much more troublesome. And we haven't seen many good examples of that. I'd be interested if people could identify some. But any new capability is going to have to interoperate with the old, in my opinion. And if it's a design constraint that you must continue to be backwards compatible with the old systems, you will likely lose some, and you could lose most of the essential degrees of freedom in coming up with a new design. So I think this is actually an area in which innovation may be possible, provided we can maintain control over the processes by which we set the interface standards to what's new. I mean, I could give you examples of how the internet conceivably could evolve and end up in walled gardens of isolated functions, or one where it could grow and by a viral process be allowed to expand, even though people thought they were doing proprietary things. That's a longer discussion. We don't have time for it today. But I think architecting change on a global scale really is much more difficult now than it was when the internet began, and I think it will become increasingly more difficult in the years to come. We may be talking about degrees of infinity here at some point. So I'd like to close my remarks by asking what the NITRD program really could do in this regard. So I, for one, I'm willing to assume that we might, uncover some kind of a structured approach or methodology that can deal with this problem. I think it's one that you heard Tom say they might be interested in looking into as time goes on. If we do have a pervasive medical records infrastructure, for example, assuming the planning comes to fruition, how many years after that will we'll be able to change that infrastructure easily? And if so, how would we make changes to it? And will there maybe at some point in the future come a time when someone determines we need a clean slate approach to that as well, and then find out there's no good way to develop one and or put it in place such that it remains interoperable with the old one? Or can we bootstrap and layer on top of the existing structure? Who and perhaps what group will know enough in 20 or 50 or 200 years from now to perform this kind of transformational task from architecture and design to implementation and deployment and evolution while the old one continues to operate in parallel? And how do we assure that we do that in a way that achieves a multi-stakeholder solution that's both technology and platform independent over time? And finally, how can we teach students about architecture and design principles for such long-term development so we develop a cadre of people that know how to do this in the future? If the NITRD program is looking for a long-term strategic thrust, it seems to me this is an excellent area to begin now, the research that can illuminate the future. So let me stop there and take questions.
I think we have time for one question, and then we'll get going because we have 45 minutes in the second panel.
I think you keyed up an excellent issue. you spoke about it in the context of networks, but in fact, the evolution of software in all genres is a key problem, and particularly in the context where the United States has more investment in old software, it can become both a competitive advantage and a competitive disadvantage. And I think that you keyed up a number of points on which important research can be done. One of them is just when do we make a decision about whether it's worth replacing or not? And I believe we can apply science to that decision and make that much more, those decisions more accurately. I think that studying the organizations which make those changes is also important. It's not just a question of looking at the code and the documentation. I do think that we should be spending money on tools to allow us to morph technology, and I think that we should also be looking at ways of writing software that's more evolutionary. So that's probably more of a comment than a question, but I just wanted to emphasize some of the things you said.
You know, I agree with that, and I would also say that while my remarks were attempting to give you specific examples that I experienced on the networking side of the ledger, my remarks were really about infrastructural capabilities more broadly, and I mean, I certainly would intend it to apply to broadly deployed systems of all kinds.
Thank you. We're going to have to go forward. We'll take more questions in the second period. Thank you very much. Our next speaker is Stu Feldman. Stu is Vice President for Engineering at Google and previously served as Vice President for Computer Science at IBM Research, where he drove IBM's long-term and exploratory worldwide science strategy in computer science and related fields. Stu is a former president of the ACM and received the 2003 ACM Software Systems Award. He's also a fellow of the IEEE, a fellow of the ACM, and he serves on a number of government advisory committees. Stu.
Okay. I want to just touch on three topics, if I may. So I will try to talk reasonably quickly, but we'll see. So the big topic, following up, by the way, on Mike Nelson's comment, Beyond Virtual is a poor bumper sticker. I hope it gets replaced. I assumed until I looked at the documentation it was about something about virtual and physical. I decided after a short while it really was just a reference to utopia in the original sense of the word nowhere. So, okay. So, anyway, the big issue that I would think is really relevant for understanding in our 5 to 10 year time frame is big data and fast interaction. You know, the need to process enormous amounts of information, extract the value from them. This is both data at rest and data in motion. In this world, the stuff keeps coming at you. The fire hose, unfortunately, is the wrong analogy. I'm sorry, it's the Niagara Falls. And you're at the bottom with your mouth open. A bad idea. Okay. Let me just say that just for purposes of discussion, nothing is interesting if the unit isn't petabytes and terabits a second and thousands and many thousands of standard processors as just your unit of operation. I will cheerily forward reference where the terabits are coming from. I'm just assuming that it'll be easy. Nice not to be in networking. Distributed computing is simply a default assumption. At the scale we're talking, everything always breaks, everything is always wrong, and those are just parts of the engineering problem. They're not some exotic. And the networking also always breaks somewhere. And users just don't like waiting, no matter what kind of users there are. There's multiple user models here. There's everything from a few deep analysts or researchers who are happy to spend months or years digging deep. And then there are the equivalent of the Google hundreds of millions of people who want an answer and expect it in 1 second. We try to deliver. The expectations change in the weirdest ways. It turns out that, for example, Google Maps customers on mobile devices are far less forgiving than people on desktops. It has to do with the fact that you just drove 20 minutes and it wasn't there. And the fact that the pizzeria shut last week is still Google's fault. If you just drove 20 minutes. So the expectations rise, the uses change, and that's what's fun. But 5 years from now, the bar of 24/7, 1 second delivery and such things as that will be viewed as of course. Of course, it's not just text, video, images, voice, and of course those all up the ante on all the information levels radically, and the networking, oh Lord. And the fact that the real-time data, some of it are structured, some unstructured, these are just givens, and the research requirements here are enormous. The current search engines are only the opening gun in this question, and everybody understands that. The fact bases are enormous. Telling the difference, coming back to a topic from yesterday, of a fact and a apparent fact, veracity is a real problem. You can do great deductions from fairy tales, but it doesn't get you anywhere. So all of these are just part of the requirement for both the research, the deployment, the understanding. And this is a world of interaction. The system learns from the users learn from the system. This is absolutely essential. Google operates, I should point out, on this mode. We look at what people do with the answers we give them and figure out whether we gave them a good answer. That's elementary. That's level 1. You can picture levels 2 through 5 coming up of what are we going to have to do. So let me raise a second topic, which is, at this scale, how do you do software engineering? How do you build the software? How do you build the systems that operate at this scale? There's the easy part, writing them, designing, architecting, writing, all that. You just need a whole new generation of tools and people with about 5 times the current IQ, and we're all set. And that's the easy part. Well, how do you test or verify systems of global scale? You just, as people point out, if you want to test the internet, you just set up your second full global internet and test it. That test bed turns out to be a little expensive, especially if you want all billion users to participate in the test. All right, all the systems I'm alluding to have this nasty problem. How do you verify? How do you test? Now let's get to the real stuff, which Bob already alluded to, which is evolution. How do you rethink, rewrite, rebuild the things? Google, for example, has had the luxury of tossing software away. We actually have rewritten the storage system 3 times, the search system, you can't count how many times it's actually been rewritten in the course of the years. Patching very rapidly reaches the end of life, but almost no one can afford doing anything else, it seems. This is a big problem. And then let me raise an issue which tends not to ever show up in the software engineering question, which is deployment, operation, support, which now that's all the data that you look at in the software engineering literature tend to have this footnote that says, testing is more than half of, is larger than coding, and maintenance operations is 4 times bigger than the sum of the first 2. That's about right. There's been remarkably little progress in what you really do in this economically challenging area, partly because it's hard to do small-scale experiments. How do you get a system up? How do you get a system up when you're editing the space station at 20,000 miles an hour and all the metaphors that we do? How do you make a change in a system that really matters? You may or may not want your remote pacemaker to go down for an hour of maintenance, as your simple example. And the problem is systems last a very long time. Hardware and software doesn't. People expect the system, whatever it is, to be there with all the funny compatibility expectations, whereas in reality you replaced every disk 4 times in the last dozen years, and the kernel has gone through 17 mods. Understanding how you do any of that, other than we'll do it at midnight and hope for the best, is very hard. And I would say that this is an area where the research base is simply absent. Then, if you're looking in systems of the sort I'm alluding to, you have all kinds of wonderful problems like non-repeatability. If the data come in arbitrary orders, and worldwide they will of course come in different sequences, and we can go to Leslie Lamport or something, or you can say we'll live with inconsistency, pick some model. All of these are very hard, and these get solved at a base level in any system of the magnitude that's needed to handle data and give answers and iterate and interact at the scale that's actually exciting. And then, how do you experiment at scale? This is a simple matter of practice. When Google has a proposed change in the search formula, after it manages to get through the first 3 or 4 hoops of is this a good idea at all, at some point that we simply divert a significant amount of traffic to use the new formula and do lots of testing. So the test is running on perhaps 1% of the total Google volume. That's one hell of a test base. In other words, you don't put up random demo code and aim that Firehose at it. This is just the easiest case that you can describe. Now imagine things much more complex, ones which involve very deep and ongoing analysis. Okay, and then I will just say that in the reverse of the usual statements, we need a lot of feedback from practice into the research base. The innovations happen in real life, in practice. The improvements, the understanding, and the replicability of them happens in a research model when you figure out why that worked at that one time, as it were. And we need much faster feedback and learning in that model. That, I believe, is one of the key links that seems to be very broken. It took a 5 or 10 year lag for things like team programming, extreme programming, and all of those things to become software engineering research mainstream, for example, even though they often work and frequently fail. And let me just raise one other little topic for just 30 seconds, which is, I'll just make a very unpopular statement, but I think in this context, I had better. If the agencies are going to get complex advanced systems to work, they need in-house competence at a level higher than almost any of them actually have. And certainly none of them have a lot. Even if you're going to be contracting out most of the work of the heavy lifting by law or by practice, you need to have people who could have done it or have done it before. Otherwise, you will not own a system that does anything you really want. Yes, this means, for example, hiring experts at market rates, which are frequently above G9 levels. But of course, the government has mechanisms for creating FFRDAs, captive consulting and such. And let me just urge that this is utterly essential for any agency that's really going to be doing these systems. And I believe every one of the agencies supporting this meeting is in that boat. By the way, this is a superb window to be shopping for such people. Industry having made, based on some of the emails I've gotten in the last couple of months, a number of errors in people who are surplus to current requirements. Go shopping now. You can get people you couldn't get a year ago and won't be able to get a year from now. Bernanke willing.
Okay, I think we're going to have to save the questions. We're really running out of time. Okay, so please write your questions down, save them, and we'll have the discussion time. Our next speaker is Doug Van Houweling, who is the founding president and CEO of Internet 2 and a professor at the School of Information at the University of Michigan. He was the chairman of the board of Merit Incorporated, a Michigan statewide computing network, when the NSF Foundation awarded it responsibility for operation and management of the NSFNet, the national backbone, in partnership with IBM, MCI, and the Michigan Strategic Fund in 1987. Doug himself is the recipient of the EduCause 2002 Excellence in Leadership Award, and he currently serves on the boards of the Merit Networks, Altarum, and Adaptee. Doug.
See if I can get this to stay up here. There we go. It's a delight to be with you here today, and it's a special honor to have a chance to speculate a little bit about how we ought to set our priorities for the future. I'd like to start by just saying that I'm going to really be focused on what Bob was also focused on, how we build a global infrastructure and maintain it as we go into the future. I want to talk some about technology. I want to talk about usage and applications. Let's start with the technology. I think all of us in this room understand that this network is not much longer going to be constrained to be a network that interconnects computers in the sense that we think about today. It will be a network that interconnects objects as well as people all over the world, especially sensors of all manner that are helping us deal with the environment in which we operate. It will become increasingly a wireless network. As it becomes increasingly wireless and increasingly sensor-oriented, it will be increasingly a network that provides ubiquitous, always connected environments in which we operate. It's going to require substantial architectural change for us to achieve that kind of a future. Require new protocols. There's a lot of work going on here, as I think everybody in this room knows, that the question of how we slide these new capabilities into the current network in a non-disruptive fashion is a very large priority, and I'll say a little bit more about that later on. But you know, it's not just going to be about the physical networking space, it's also going to be very much about how we manage the relationship between the objects and people that are using the network, and that's going to require a whole new set of infrastructure in the area of authentication, identity management, so that people who operate using the network are able to participate in whatever organization globally they need to participate in and interact with whichever sensors globally they need to interact with. Interestingly, the population that most lives in this world today is a lot younger than we are, and we need to start thinking about that. Now, we've already talked a little bit about the implications of this for healthcare. I think they're extraordinary and extremely promising because, of course, this sensor-based wireless ubiquitous network has enormous promise for delivering better care, maybe even more importantly, actually enabling better health. Because let's face it, folks, we're not going to solve this problem by better care. We're going to have to solve it by being healthier. And we need to understand how this sensor-based collaborative network is going to help with that. But I would like to point out that there will be a further transformation that is, I think, today still very much just a gleam in the eye, perhaps only of the science fiction writers. As we increasingly deploy sensors to facilitate and assist individuals in the health arena, those same sensors will become part of the standard interface between human beings in this system. And we will wind up not having cochlear implants just to hear what's going on outside, but to interact with the systems that are part of this network. There's an opportunity here for innovation that simply overwhelms the kind of innovation that we have been talking about up until this point. And I think for this nation, the key is to think about what type of civic cyber infrastructure we will need to support that future. The merge of information technology, healthcare, and bioengineering to a totally different type of network environment. Now let me just say a few words about how we might manage to make progress in this direction. I'd like to suggest that university campuses can be the foundation of this innovation. Think for a moment about what one of our research universities looks like. It has a healthcare center. It has a very high technology on-campus network environment, which increasingly is providing wireless. It has typically some of the most advanced medical care networking systems that are available, although not always very well integrated with the rest of the world, as you all know. And it has a surrounding community, which is also not well connected typically to the campus, but it could be. We could think of these environments as leading communities of innovation to the future of how we're going to manage and create the cyber environment in which we are all going to be living. Finally, I'd like to suggest that it's not enough for government to just underwrite the research and innovation. It's already been said here that the hard problem is how we deploy and support. I think we've had a notion up until now with this infrastructure that we could depend on the invisible hand of private industry to manage that hard problem. I think that's a misconception going into the future. I think there needs to be a partnership in which the government plays a role. I'm not suggesting here that I know what that role should be or how it should be managed. In fact, I'm suggesting that this is in itself a very important subject for research. That we need to understand how we link the technical, social, and political systems in a way that allow us to move forward and once again in this area have this nation provide leadership in the way we use information technology in our lives. Thank you. Questions? We have time for questions. I was fast enough. Suggestions? Yes.
I just have a comment, and Barbara actually may have more of the facts. I have a recollection that the Blacksburg Electronic Village around Virginia Tech tried to exploit the notion of universities as microcosms, and they ran into some legal problems with the state telecom regulations. So I think your point about doing research into the larger context so that we can get by the kinds of barriers that shouldn't exist may be very apropos.
Do you have anything you want to add to that, Barbara?
No. In my diligent 6 months of being in Blacksburg, I haven't yet encountered that, but I know that there is, for a community located where it is, there is an awful lot of electronic smarts and infrastructure in the community. And it may be that when the experiment was tried, as I understand it was about 10 years ago, yes, things were different. That is,
yes.
I would like to hear Doug's comments on that.
No, I think that's right. I would also say, though, that the fact that the information technology innovation folks who were responsible for that at VPI explicitly try to include private enterprise means that there's a stronger partnership in that area of Virginia than there is almost anywhere else in the state. It's really quite extraordinary.
Fenian Magadan, In Europe, they're very much involved in projects between research and university and industry. There is the huge Global Village project.
Yes.
IBM is part of that. And IBM Europe, and the telecommunications ministry in France, just south of Paris. Also NIST here is involved. This is a much more challenging situation than this habitat kind of environments we're talking about, because it involves enabling normal people. I didn't mean to say normal. I meant people without physical challenges, okay, to also have access to transportation, buildings, and so forth. It may be in the United States is much easier, but in Europe there are real challenges, because I have a very elderly mother and she uses, let's say, a tri-wheeler. Try to do this in the heart of Athens. It's a real challenge. And so this Global Village initiative may not have produced real discoveries, but it is very much addressing the questions you posed. New architectures for network scalability and sustainability and all that.
Right, and it would be really quite wonderful if you could be with your mother virtually when she's seeing the doctor or when she's encountering some of these challenges, and be able to be helpful to her even though you can't be on the site. And I think all of us who have elderly parents wish we had more of that capability. And I think this technology provides the opportunity for that if we could find a way to get it organized more effectively. Yes, Myron.
Yeah, one way to address maybe the legal aspect, but I think also help us to move more effectively forward, is to look at scientific communities as examples.
Yes.
And I believe that you will be able to abstract from what they need and what needs to provide, what we have to provide them with, to all the other things that we are talking here, which are applicable to the general public. So rather than labeling it, how do I help my elderly mother to do something, I think if you look at what the LHC is trying to do with remote sensing to keep the biggest machine on Earth working, you will identify a lot of the stuff that you need, and here you can work, you don't have to deal with legals, and you have very engaged users that need it. And you can do it at scale for science, not at scale of Google, but in a very nice scale. So rather than trying to mimic the outside environment, get more engaged with the scientific activities, and I can assure you, you will find a lot of what you're looking for.
Yeah, and I think we've learned that lesson to some extent already, Maron. The fact is that we deployed this internet technology initially for scientific purposes. It turned out to have much broader purposes. And even today, the advanced internet technology that's shared by the universities and the scientific community is being used by the arts. It's being used in a whole variety of ways. The problem, of course, is how you actually get that technology bridged across to the broader community.
I would say if it's just the quality, if you do it right and it works, people will adopt it. But I think it's a much easier sell to say that I'm doing healthcare than I'm doing high energy physics, and therefore I will create the technology. And I think this is the barrier that we have to figure out how to overcome.
Okay, thank you.
Thank you very much. Just as an aside, I just want to mention that something that's striking me in these presentations is that not only technical problems that we think of as pure science, but technical problems involving people in the equation are becoming more and more relevant. So our next and final wrap-up speaker is Susan Graham, who is the Pahang Chen Distinguished Professor of Electrical Engineering and Computer Science, Emerita, and a professor in the graduate school at UC Berkeley. Her research spans many aspects of programming language implementation, software tools, development environments, high-performance computing. Susan is a recipient of the Harvard Medal, a member of the National Academy of Engineering, a fellow of the ACM, the American Association for Advancement of Science, the American Academy of Arts and Science, and a longtime friend of CPLAN. Susan.
Well, I'd like to bring us back to the topic of beyond virtual. And I have to tell you that when this group was preparing for this meeting, we had a phone conversation to find out what one another we're going to talk about, and we spent most of that phone call trying to understand what beyond virtual means. To me, and then I talked with Jeanette Wing yesterday, and I told her about that, and I said, well, what I'm going to talk about is cyber-physical systems. And half an hour later, she came up to me and she said, well, maybe we should be calling this cyber-physical systems. So let's hold that thought, and I'll return to that at the end. But I do want to talk about cyber-physical systems, by which we mean the integration of computation with the physical world. And we've been talking about that a lot for the past few days, yesterday and today. If you think about Philia's talk about assistive technologies and healthcare and safety, and her instrumented room, that's all cyber-physical. Okay, it's the mixture of computing and communications with the physical world, using a variety of sensors. Now, that's, I would argue, plowing new ground. In other words, she's talking about an area of research, as have a number of other people, which is facilitated by the changes that are going on in networking, in big data, in the availability of sensors, in miniaturization, that enable a new way of tackling a societal problem. Okay, so a new approach to problems which were not enabled by the technology in the same way. We actually have a long history of cyber physical systems, and they're much more in the realm of embedded computing. So I'm going to take examples both from this healthcare that Philia brought up and from surface transportation, because when I think traditionally about cyber physical systems, I think about automobiles and the growing number of computers that are embedded in automobiles that control all the aspects of the operation of the automobile. And that's cyber physical systems, but that's the traditional view of it. The computers are invisible. It's only we techies that really know they're there, and they're gradually augmenting the capability of the automobile to do the same thing it did before. You know, it's a vehicle for moving people from one place to another on highways and paved roads and so on. Now, potentially, the fact that we now have all these other technologies makes cyber physical systems a transformative paradigm-shifting change in not only the way we can do new things, but the way we do old things. And, for example, people in transportation are talking about being able to have more dense traffic on the roads because you can use sensors to not only know what's going on around the car, but to help to navigate it at closer distances, shorter tolerances, and so forth. This is actually potentially a huge change, like networking was. We, again, didn't see it so clearly at the beginning as we can looking back at it. This potentially has the same character. It's a set of technologies and opportunities that affect all the agencies. You just heard Tom talk about smart grids. They're all cyber physically enabled. Smart buildings. There are obvious applications in the military sphere. there are applications not only in health but in the biological sciences generally. So it's a unifying perspective on the future of IT and communication as well. So let me give you a couple of examples from this space. What I'm arguing is we need to rethink, not only take advantage of new opportunities to new things, but think about how these new technologies are going to affect old things. There was a wonderful editorial in the New York Times a few weeks ago, had nothing to do with IT. I wish I'd saved it, but I hadn't. And it was talking about the fact that as systems of all kinds develop over time, they have a strong legacy component and they're evolutionary, so that where you started and the things you did early on continue to affect where you are today. Bob talked about that some in the evolution of the Internet, that for various reasons, legitimate reasons, we can go back and we can look at the origins and we can see a lot of traces of that in the way we do things today. So if I go back to my transportation application, and you think about the way cars operate on roads, we have conventions for fairness and for sharing, and we have traffic lights. Okay, traffic lights say, whole group of cars stop, another group of cars goes, then they stop and the other group goes. Enormously inefficient. Inefficient in our time as we sit there and wait for the light to change. Inefficient in the use of energy. Inefficient in the use of the road because of the fact you're not traveling on the road and that's what it's for, you're standing still. We made minor modifications. We have right turn on red and things like that. But it's basically a legacy system. Given all this technology, if you look at people, the way people move themselves in a plaza still has fairness, still has the ability to turn and go in various directions, but they're all moving all the time. Maybe with all of this technology, we need to step back, or we have the opportunity to step back and rethink these basic mechanisms and maybe find a more efficient way, an evolutionary way. We still use the cars, we still use the roads, but we do it in a way that's cyber-enabled, if you like, depending also on the fact that we've got all this information available, both legacy information and immediate information, which is going to tell us how we do that, and it's still all safe. Here's another example from transportation. One of the things we want to do as a society is to lower the number of accidents to pedestrians by cars, in other words. And so let me talk about people stepping into traffic. Okay? We have the technology potentially to replace seeing eye dogs by electronic. Thank you. I'm developing. Replacing seeing eye dogs by the electronic equivalents that would keep people from running out into the road. We could use that whether you were sighted or not. I mean, it's the equivalent of having somebody grab your arm and pull you back. How do you do that? We're all going to be instrumented. People are already instrumented. They're going to be much more instrumented. Our GPS cell phones are the first step. Our jackets that allow us to have our MP3 players wear on us are already available. We can assume that not only will the environment around us be instrumental, but will be instrumented. Okay, if I want to keep somebody from going into traffic, do I instrument the people or do I instrument the environment around them? I want a virtual fence to come up. Do I have that fence by somehow locking my knees so that I actually can't run into the street? Or do I do it by having my guided automation system divert the traffic so it doesn't hit me? All of these things are opportunities. All of them exploit the technology. None of them are like anything that we've done so far. So let me move to how we might live in this world and what are the things we might do. Miron said yesterday in a somewhat different context, should we be asking ourselves whether we need to change what we do given the vast increases in users and in capability? So I think we need to ask ourselves that question. The networking community is currently having a discussion of their own research agenda. And one of the things they're doing is they're asking the question, suppose we started over. Bob just explained why we can't start over. But suppose as a thought experiment, we started over and we designed a new internet from scratch. Given all the things we know and given all the technological things we have now that we didn't have when we started, what would we do? Okay. They're not doing that because they think they can start over. They're doing that because it informs your thinking about the evolution to consider what the right decisions would be in the current context with the current capabilities. So one of my recommendations to the NITRD agencies is have some projects in all arenas in which researchers ask the question, what if you started over with the current and envisioned technologies and tried to figure out how you would deal with your problems. They're research projects. They're grounded in real societal problems. The second thing that we do, and this came up over and over again, these cyber-physical systems are going to have people as important components, just as a number of people have pointed out. We have a tendency, I think we can solve the problem of is it research if we go to the social scientists. Our other problem is we forget that there are experts that know more about components of the problems we're trying to solve. So we were talking yesterday about collaboration and how do we get multidisciplinary problems. There are people whose life work is to study how groups interact and how they're business people, for example, who worry about collaboration. We should go to them when they're the ones that can answer our questions, just as we should go to the sociologists when they're the ones that. And it's a habit you have to acquire that many of us don't have. We use ourselves as human subjects. And then finally, I just want to address very briefly how do we engage the mission agencies? This was the question that I asked yesterday. Mission agencies have their missions. They have things they have to accomplish. Many of them are shorter-term goals shorter-term plans than the luxury that I would like to think the research community has. I'd like to see the mission agencies express long-term goals with their short-term plans. In other words, share with us where they want to be in 10 years, where they want to be in 15 years as they plan how they get through the next 5 years. And share that with the research community so that we can begin to contribute the fruits of our research that might inform their 5-year plan 5 years from now.
Thank you very much. I think we have time for one question, and then we'll go to the 15-minute break.
I really liked your comment about the mission, understanding the mission of the different agencies. One, of course, realistic problem is that their mission changes with new technologies that we produce. Mm-hmm. And therefore, that goes back to your other comments yesterday about, mechanisms of better communication. Because I think this is at the crux of the matter. There are not very good mechanisms of communication at all levels. And I just wanted to end, I don't want to trivialize your comment about protecting somebody from crossing the street, but there are projects, a Dartmouth colleague of mine was doing with cows in Vermont, put in wires that give you a shock so the cows don't go on the street.
Right.
But there could be something human-centered. Yeah, thank you.
I just intended that as an example.
Sure, it's a great example.
I think we're going to stop now because we're on a really tight schedule. We have another 45 minutes in a round table, and we're looking forward to animated discussions with the rest of you.
Thank you.
Thank you to everybody on the panel.
Yeah, I'd like to add my thanks to the panel as well. Excellent job. Another stimulating discussion this morning. We're going on break now for 15 minutes. We'll start back again at 10:15. We'll have our roundtable discussion. I believe we'll have an hour and 15 minutes for the roundtable discussion when we come back. So plenty of time for your questions when we come back from the break. So take care of those bio needs, get some snacks, and we'll get right back to it.